Hello students, let us continue our discussion regarding the Ohm's law and let us try to prove how the Ohm's law V is equal to IR come into existence. Let us take a conductor, a simple conductor whose length is L, area of cross section is A. Let us connect this conductor to a battery of voltage V. We know that when this battery is connected, this potential difference across its terminals V and 0 gets distributed across this conductor through this connecting wire, and because of this potential difference of V and 0, electric field is set up inside the conductor. Here one important point you need to be remembered is this electric field inside a conductor is always 0 only in the electrostatic case. That means in the electrostatics, when we are studying, we tell that electric field inside a conductor is 0, but here in the current electricity, as all the charges are trying to move, the electric field inside the conductor will not be 0. There the electric field is 0 because simple reason, the charges will try to rearrange themselves in order to give the net electric field inside the conductor to be 0. Let's take an electron inside this conductor and we'll try to analyze its motion. This electron will experience a force of this much. This force is given by the formula charge of electron into value of E. So I can write this F as force equal to Q into E, where force is equal to mass into acceleration, that is nothing but Q into E. Charge is electron's charge, and E, mass into acceleration, can be written as a drift speed upon the time. So, and from here this electric field for this conductor is given by V upon L. Substitute V upon L here. So we just try to do this derivation in the class. V d by T is equal to E into V upon L. Drift speed is given by the famous equation I upon number of electrons into charge of electrons into area into T is equal to E V by L. Try to rearrange these terms in such a fashion that you get V, all the V terms one side and all the other terms one side. Let's rearrange this one. V equal to, I think you might not be able to look at that color, I'll be rewriting that one. V equal to I into, let's arrange this one, M by N E square into T into L by area. I just purposefully kept L by A like that. V is equal to, this is a famous equation, V is equal to I into R. This for a constant length, area, time and electric charge of electron, number of electrons and mass, this is completely a constant, and this resistance is given by this one. Resistance is equal to this mass upon Na square T is a property called resistivity, rho L by area. This is a famous equation of Ohm's law, where resistance is given by rho L by A. Rho is called resistivity, R is called resistance, L is length and A is the area of cross section of the conductor. Let's get this point clear here. This wire which is connecting this conductor to pass this voltage across this conductor, the voltage is never been lost. Whatever the voltage is there, that voltage is being supplied by this connecting wire If the voltage here is V, the voltage here has to be maintained V. The current is passing. The property here we use is the potential difference between these 2 points, V minus V, is equal to current into the resistance of this connecting wire. Current is passing, current is not zero, but the resistance of the connecting wire has to be zero to get this, to satisfy this equation. Therefore, we can conclude one point from here: resistance of connecting wire to be zero. Let us continue in the next class with the network solving. Thank you.